I'm Neil Armstrong, commander of the Apollo 11 mission.
It's one small step for man, one giant leap for mankind.
I'm working with the American Institute of Aeronautics and Astronautics on the Evolution of Flight campaign. This campaign marks the 100th anniversary of flight and lays the groundwork for the next 100 years of innovation in aviation and space technology. The IAA and NASA Connect are excited to give you the opportunity to learn about the aircraft design process. You'll see a really cool experimental aircraft. You'll observe NASA engineers and researchers using math, science, and technology to solve their problems. In your classroom, you'll test and improve wing designs. In our instructional technology activity, you will become an employee of Plane Math Enterprises to design and test aircraft using a computer. So stay tuned as host Dan Giroux takes you on another exciting episode of NASA Connect.
Hi, welcome to NASA Connect, the show that connects you to math, science, technology, and NASA. I'm Dan Giroux, and today I'm at the National Air and Space Museum in Washington, D.C. Over my shoulder is the Wright Flyer. This is the first manned airplane to fly under its own power. It was built by the Wright brothers. This is the Bell X-1, the first plane to break the sound barrier. Notice how sleek its shape is. And this is the X-15. It's the first airplane to fly into space. Notice how closely shaped it is to a rocket. There are tons of planes here. Let's take a look. Before we continue our show, there are a few things you and your teacher need to know. First, teachers, make sure you have the lesson guide for today's program. It can be downloaded from our NASA Connect website. In it, you'll find a great math-based hands-on activity and a description of our instructional technology components. Kids, you'll want to keep your eyes on Norbert, because every time he appears with questions like this, have your cue cards from the lesson guide and your brain ready to answer the questions he gives you. Oh, and teachers, if you're watching a taped version of this program, every time you see Norbert with a remote, that's your cue to pause the videotape and discuss the cue card questions. Today's show is about the future of flight. But before we talk about the future, what is commercial flight like today? And what current technologies are being used by pilots?
Hi, I'm Connie Tobias, and I'm a pilot with U.S. Airways. This modern Airbus aircraft gives us the tools we need to navigate safely and efficiently through today's complex air traffic control system. The Airbus aircraft has an array of computer screens that give the pilot information about performance, navigation, weather, and the location of other aircraft in our airspace. About 10 years from now, over 3 million people will be flying every day. That's about 1 million more than today. Updated computer technology and faster aircraft will be needed to deal with this increase and to reduce the travel time between destinations.
Thanks, Connie. Now that we know what pilots have to keep in their minds with today's aircraft, let's consider the future of flight. Have you ever wondered what the airplanes of tomorrow will look like, or how fast they will travel? Will tomorrow's planes travel into space or beyond? On today's show, we're going to learn how NASA researchers and engineers are using geometry and algebra to design, develop, and test future experimental airplanes.
What is an experimental plane?
Experimental planes, or X-planes, are tools of exploration that come in many shapes and sizes. They fly with jet engines, rocket engines, or with no engines at all. which means NASA flies not only the fastest airplanes, but the slowest as well. Some planes are too small for a pilot, and some are as large as an airliner. The research conducted on experimental aircraft today gives us a glimpse into the future. NASA is developing one of the fastest experimental X-planes ever. It's called the HyperX.
What is the HyperX?
The HyperX research vehicle is an experimental plane that uses this really cool engine technology called the scramjet.
Go for main engine.
Unlike rockets, such as the space shuttle main engines, which must carry both fuel and oxygen, the scramjet will only carry hydrogen fuel. It will take in oxygen out of the thin upper atmosphere as it travels along. We call this kind of engine an air breather, and it will allow the HyperX to fly at incredible speeds. In fact, the HyperX will fly at about 3,020 meters per second, which is about 6,750 miles per hour, or Mach 10.
What does Mach number mean?
Mach number represents how many times the speed of sound a vehicle is traveling. For example, Mach 1 equals the speed of sound, which is approximately 302 meters per second, or 675 miles per hour, at an altitude of 100,000 feet, which is the test altitude for the HyperX. Mach 2, which is twice the speed of sound, would approximately be 604 meters per second, or 1,350 miles per hour, at an altitude of 100,000 feet. Mach number are used by NASA researchers to describe the speed at which a plane is flying. Let's use algebra to show how to calculate the Mach number of the HyperX, flying at 3,020 meters per second, or 6,750 miles per hour. This algebraic equation shows that the Mach number equals the speed of the plane divided by the speed of the sound in the air, where m is the Mach number. V is equal to the speed of the plane, and a is equal to the speed of sound in the air. If the speed of the plane is 3,020 meters per second, and the speed of sound at 100,000 feet is 302 meters per second, then what is the Mach number? That's right. 3,020 meters per second is about Mach 10, or 10 times the speed of sound. We'll learn more about Mach numbers later in the show. But first, let me tell you about the HyperX. The HyperX is designed as a flying engine, which means the airplane and the engine are one unit. The unique shape of the airplane develops the lift necessary to keep the plane up in the air, so it doesn't need wings to produce lift. The entire undersurface of the airplane is designed to act as part of the engine. In order to test the scramjet engine, the HyperX is launched by NASA's B-52 and boosted by a rocket to its testing altitude. It will then separate from the rocket, and the scramjet engine begin its test flight. So, have you ever wondered what goes into designing an experimental plane, such as the HyperX? I know I have. I'm here at NASA Langley Research Center in Hampton, Virginia, to talk to Dr. Scott Hum.
What are the steps in designing an aircraft?
How does the mission requirements of an aircraft determine its shape?
Why are wind tunnels important in testing aircraft designs? Why?
Hi, Dan.
Hey.
HyperX is definitely a very exciting program. In my job, I use wind tunnels to determine the flying characteristics of a variety of different vehicles that fly many times faster than the speed of sound, like the HyperX. Here, the exciting part of the HyperX program is that it's truly pioneering. That means no one's ever done it before, so we have to blaze the trail.
NASA sure has blazed many trails. How do they do it?
The first thing you have to do when blazing a trail is to determine a mission, or where you want to go. We develop a set of requirements for the vehicle, and then we begin a process of designing a vehicle to meet that mission. Have you ever been to an air show to see a bunch of different airplanes?
Yeah, some planes are short, some are long and slender, some fly slow, and some fly fast.
You're right. They look and perform differently because they were designed to satisfy different missions. For the HyperX program, our mission is to have it fly very fast. We also want to be able to control it, and we want it to be able to propel itself. You see, NASA has many years of experience testing fundamental shapes to understand and document how those shapes, we call them geometries, respond to the airflow at various speeds. Let me show you. The Apollo capsules used to bring the astronauts back to Earth after their trips to the moon were designed as blunt bodies. This is because this particular shape has high drag, a force that slows an object down.
The blunt body creates the drag needed to deploy the drogue parachute, followed by the main parachutes. The force of drag then gently lowers the vehicle safely to the Earth.
NASA had to design a vehicle that would slow down to speeds where it was safe to deploy the parachute for landing in the ocean.
Okay, I get it. But what about other shapes?
Well, we know that slender shapes, like the Concorde, have less drag. A vehicle that has to propel itself, like the Concorde or the HyperX, has to have an engine with enough power to overcome the vehicle's drag. So if you were designing the HyperX to propel itself and fly really fast, would you want a blunt body or a slender body?
I'd want a slender body.
That's right. The HyperX is designed as a slender body because it has less drag for the engine to overcome. You're well on your way to becoming a conceptual designer, Dan.
I am? Sweet. So, once you've decided on a mission, what's next?
Detailed design. A conceptual designer makes decisions like the one you just made to find a geometry that will meet the mission requirements. The detailed designer uses tools such as CAD or computer-aided drafting to turn ideas into drawings. These drawings help us work out the details of how to design parts of the HyperX, like the engines, the control surfaces, the fuel tanks, and so forth. Once we have an initial design, we begin a process to improve it. We compare the design of the HyperX to other vehicles with similar characteristics. We may need to make changes to the geometry to improve the performance.
How do you know if you need to change the shape?
One way is conducting wind tunnel tests. You see, during the design and computer modeling stages, we extensively used our wind tunnels to quickly screen our HyperX designs. And then, the wind tunnel tests helped us to determine the best design and to understand how the vehicle will fly.
Okay, so what is a wind tunnel?
Wind tunnels are devices that allow us to move air over a scale model of a flight vehicle, like the HyperX. We use models instead of the real vehicle because they're smaller, less expensive, and easier to change if needed. This is NASA Langley's 31-inch Mach 10 wind tunnel. This tunnel can get the air moving up to 10 times the speed of sound. Once we place the model of the HyperX in the wind tunnel, we make measurements to determine how the air interacts with the model. At the nose of the vehicle, the flow near the surface is very smooth. We call it laminar. But as the air moves down the length of the body, it changes and becomes turbulent. You can see this natural process by looking at the smoke after you blow out a candle. After you've blown out a candle, you'll notice that the smoke near the candle rises smoothly. That's laminar flow. But farther away from the candle, you'll notice it becomes rough and irregular. That's turbulent flow. Normally, we think of laminar flow when designing aerodynamic shapes. We want the air to flow smoothly around them. However, for the HyperX geometry, we require turbulent flow.
Why would you want turbulent flow on the HyperX?
In order for the scramjet engine to work properly. You see, turbulent airflow enhances the mixing of the air with the hydrogen fuel for better engine performance. Turbulent airflow is created by a device called a trip located underneath the belly of the HyperX. Using the wind tunnel, we tested several trips with different shapes or geometries to see which one worked best to change the airflow from laminar to turbulent. Our wind tunnel test determined that this triangular-shaped trip was the best design for creating turbulent flow for the scramjet engine on this vehicle.
How do you test the scramjet engine?
We have specialized wind tunnels capable of testing scramjets, but the ultimate proof of the HyperX is flight testing. That's the last phase in designing an aircraft. NASA conducts all of its flight tests on aircraft at the NASA Dryden Flight Research Center in Edwards, California.
Thanks, Scott. We'll visit NASA Dryden Flight Research Center later in the show. But first, join me in Dan's Domain, where we'll use technology to prepare for today's math-based, hands-on activity. Welcome to my domain. In just a minute, we'll get to the hands-on activity, which will require that you use different shapes in designing airplanes. Before we do, let's take a look at Riverdeep Interactive Learning's Destination Math tutorial. It's available free to NASA Connect educators. You can get to it from the NASA Connect website. It's part of the Mastering Skills and Concepts 3 section of Destination Math. With this lesson, you'll explore the geometric and algebraic characteristics of basic shapes. Teachers, this is an excellent tutorial that can give your students information and assistance as they prepare to do the hands-on activity for the show. In this tutorial, Digit explores parallelograms, trapezoids, and right triangles while examining the flags of some of the countries in the United Nations. Many thanks to Riverdeep for providing NASA Connect with this exciting instructional technology enhancement to our show. Now, let's do an aircraft design activity which you can do in your classroom.
We're from Pulaski Middle School.
Here in New Britain, Connecticut.
NASA Connect has asked us to show you this show's hands-on activity.
Here are the main objectives.
You'll use algebra to calculate wing area and aspect ratio. You'll use a portable glider catapult to analyze wing geometry. You'll design, construct, and test an experimental wing. And you'll work in teams to solve problems related to wing design. The list of materials you'll need for this activity can be downloaded from the NASA Connect website. The class will be divided into groups of 4. Each group will use a portable glider catapult, or PGC, which your teacher made previous to this activity.
Good morning, boys and girls. This morning, NASA has designated this class as Aeronautical Engineers in Training. Your job is to test current wing designs based on distance traveled, glide, and speed observations. From your analysis of the data that you collect, you will have the task of designing and testing an experimental wing to achieve maximum distance traveled.
First, cut out the templates for the fuselage, wings, and horizontal stabilizers. Place the templates on the meat trays and trace around the templates. Cut out the shapes. Tape a piece of masking tape to the nose of the fuselage to prevent the nose of the fuselage from breaking. Students will calculate the wing area, the wing span, the root chord, the tip chord, and the average chord for each wing. The average chord can be calculated using this formula. Next, have students calculate the aspect ratio for each wing using the formula wingspan divided by average chord. Record all values onto the data chart. Prep the launch area by measuring 12 meters from the PGC. Mark the distance at 1 meter intervals. Place tables or desks of equal height to the launching line to elevate the portable glider catapult. Place a book with a height of approximately 5 centimeters under the front portion of the PGC. Select a wing shape to test. You will be testing 4 different shapes: delta, oblique, straight, and swept back. Attach a small binder clip to the aircraft to give it some weight in order to achieve maximum distance traveled. Position the aircraft on the PGC. Using a rubber band, pull the aircraft to the launch position, then announce,
"Clear the flight deck for aircraft catapult."
7 November, go.
5, 4, 3, 2, 1, launch!
You will conduct 5 trials for each wing shape. Measure the distance traveled in centimeters and record the value onto the data chart. Record your observations on glide and speed ratings using the scales provided from the lesson guide. From the data collected, each group will design and construct their own experimental wing. Design your wing to fly farther than the original test wings.
Okay, now, how successful or unsuccessful was your experimental design? What were the factors? Rusamy.
Mine had a lower aspect ratio.
Bakeword.
Mine had a better swept back wing.
Special thanks to the AIAA Connecticut section and the AIAA mentors who helped us with this activity.
Thanks. We had a great experience today. And we encourage teachers to visit our website to learn more about the AIAA mentorship program in your area.
Okay, we've learned how geometry is important in designing an experimental aircraft. We've also learned some steps in the aircraft design process. But there's still one more step to go. Scott mentioned earlier that the last stage in designing an aircraft is flight testing. Well, the lead center for flight testing is NASA Dryden Flight Research Center in Edwards, California. Let's take a look and see what they're doing with the HyperX.
How will the HyperX reach its test altitude?
How do the HyperX engineers collect their research information?
Why is algebra important in HyperX research?
Hi, I'm Lori Marshall. I'm a research engineer in the aerodynamics branch here at NASA's Dryden Flight Research Center. I'm one of the engineers responsible for getting the HyperX ready for flight. In order to do this, we perform tests on the vehicle to ensure that the instrumentation system will measure the necessary data.
We make sure that the control room is set up properly to record this data during flight. We also perform inspections of the HyperX during assembly and testing to ensure that the systems are operational and that no damage has occurred. You see, the HyperX is a thermal protection system, similar to the Space Shuttle. The exterior is covered with special tiles that allow it to withstand the high temperatures of high-speed flight. If any of the tiles were damaged, not only would the vehicle's structure be compromised, but the aerodynamic shape that we've tested during the design process could also be altered, and this could affect the flight.
How do they flight test the HyperX at such high speeds?
Great question.
The HyperX is a very small vehicle, about the size of 2 kayaks side by side. As Scott told you earlier, it will fly at about Mach 10. Now, because of its size, we only have enough fuel for use at the test conditions or when the HyperX reaches Mach 10.
How do you get HyperX to reach Mach 10?
The HyperX is attached to the nose of a rocket. The rocket is mounted under the wing of a B-52 jet. Let me explain what happens. The B-52 takes the HyperX, which is attached to the rocket, up to a preset altitude and speed, and releases it. Then, the rocket ignites and flies to an altitude of approximately 100,000 feet, traveling to the test conditions. Next, the HyperX separates from the rocket and the scramjet engine ignites. This is when the flight test begins. The HyperX generates over 600 measurements that are sent to the control room during the flight. These measurements allow the research engineers to determine the success of the flight. Each engineer can access their data on specially designed displays, which are also recorded for post-flight analysis.
How do they analyze all these data?
Well, we use several different methods, but algebra is the foundation for all of these. We use algebra throughout the design, flight testing, and post-flight analysis phases of the experiment. The Vehicle Stability and Control System is a good example of how algebra is used during flight testing. For example, take a seesaw. A seesaw consists of a board and a pivot point, or fulcrum. Suppose we have Norbert on one side of the seesaw and Zot on the other side. Here the seesaw is not balanced.
How do you balance the seesaw?
Well, to balance the seesaw, the product of the weight and the horizontal distance on the left side of the pivot point must equal the product of the weight and the horizontal distance on the right side of the pivot point. By moving Norbert on the left side of the pivot point closer in, you can see the seesaw becomes balanced. In mathematical terms, the weight of Norbert times his horizontal distance to the pivot point is equal to the weight of Zot times his horizontal distance to the pivot point.
Now, in the case of the HyperX, the flight computer controls the wings and the tails to keep the vehicle flying and stable throughout the experiment. If not for these calculations, we wouldn't be able to fly and get the necessary data.
Have you flight tested the HyperX?
As a matter of fact, we did. Unfortunately, like many experiments, this one didn't go as planned, and the HyperX never made it to the test conditions. Sometimes, when performing experiments, unforeseen events can occur.
However, we were able to receive data from the HyperX before the test was terminated. We will use this data to successfully flight test the HyperX again and achieve our mission of testing scramjet technology.
Wow, if the HyperX program is so successful, how will it affect the future of flight?
Well, let's see. Recently, I flew from NASA Langley in Virginia to NASA Dryden here in California. It took about 5 hours. If commercial aircraft were using the same technology used on the HyperX, my flight time would have been reduced to 30 minutes.
If you ever plan to go into space, the same technology would allow for larger cargo capacity, so space travel would cost less. This technology would also allow for reusable vehicles at a much lower cost. This means we could see more launches and more exploration of space.
Thanks, Lori. For the next couple of minutes, we're going to take a look at a website that will reinforce this show's hands-on activity you just saw. It's called Plain Math, and it's produced by InfoUse in cooperation with NASA. We're going to the Museum of Flight in Seattle, Washington, where students from TT Minor Elementary School will help us show you what the Plain Math website looks like. From Dan's domain on the NASA Connect website, go to plainmath.com. Click on Activities for Students, then choose Plain Math Enterprises. You'll need to visit each of the 8 training departments. Each section gives important information about aeronautical principles and terminology. There are a number of geometry and algebra-related math concepts, and you'll also find plenty of interactive activities that help you understand the concepts presented in the website. The experts will guide you through training as you prepare to design an airplane based on certain requirements. When your training's complete, enter the design department, where you meet your client before beginning the design process. Then you'll design the size of your fuselage and wings. The building department will make a prototype, which you'll test in a wind tunnel. Based on these results, you'll choose an engine for your plane. There will be a flight test to see if your plane can take off and reach its cruising speed. If it succeeds in taking off, you'll get results on how your plane flies under different conditions. Based on your results, you can either make adjustments to your plane and retest it, or present your design to your customers. Well, that's plain math. Special thanks to the Museum of Flight and our AIAA student mentors from the University of Washington. Teachers, if you would like a student mentor to help you in your classroom, find out more on the NASA Connect website. Well, that wraps up another episode of NASA Connect. We'd like to thank everyone who helped make this program possible. Got a comment, question, or suggestion? Email them to connect@larc.nasa.gov. Or pick up a pen and mail them to NASA Connect, NASA Center for Distance Learning, NASA Langley Research Center, Mail Stop 400, Hampton, Virginia 23681. Teachers, if you would like a videotape of this program and the accompanying lesson guide, check out the NASA Connect website. From our site, you can link to the NASA Educator Resource Center Network. These centers provide educators free access to NASA products like NASA Connect. Or from our site, you can link to CORE, the NASA Central Operation of Resources for Educators. For information about other NASA instructional resources, visit NASA Quest at quest.nasa.gov. So, until next time, stay connected to math, science, technology, and NASA. See you then.
We want the air to flow smoothly around them. However, for the HyperX geometry, we required turbulent flow. I screwed that up.
Let's try that one more time.
And now you have to work, huh?
Here are the main objections. Oh, I said that wrong. And the objection is objectives.
Today, I'm one of the I was that close. I was that close, and I stumbled.
So, have you ever wondered what goes into designing an experimental X? No.
Well, let's see. Too early?
It's the first airplane to fly into space. Notice how closely it's shaped to a rocket. There are tons of planes here.
Wow! Oh, no.
Traveled, glide, and speed observations. You will, oh, I'm sorry. That's what I do when I'm nervous.
My belly itches. My stomach itches.
We're out of here. I have donuts.